Welcome back. So one very important contextual application of derivatives is the study of objects in motion. So we could put various stories to this situation. It could be you are in a car driving down a straight road. It could be you are walking down a long straight sidewalk. It could be even just a mythical particle moving along a number line. But we're describing motion in one dimension, and that means that whatever it is that's moving can move in two directions, forwards and backwards. Now, forwards might mean to the east, while backwards could be to the west. Forwards could mean moving up off the ground, and down backwards could be down toward the ground. It could be north and south, or left and right, but just two directions. And so we just typically call those directions forward or backward. And we can graph that information out on a piece of graph paper. If I know enough information to know when and where the object is, I can draw that on some graph paper. And I've got a situation like that here. Very simple drawing of a distance time graph. Let's put a story to this. Let's suppose that someone left their house, walked a good distance to their friend's house, but their friend lives on the same street as they do, so they only had to walk in a straight line to get there. And they stayed there for a little while, maybe a few hours, and then they proceeded to walk back home. And their graph might look like this. So I could ask you a few questions to start and see if we can read the graph properly. I could ask you things like, how many miles did they walk to get to their friend's house? Well, since the graph is measuring their distance from home, it looks like the farthest they got from home was 6 miles. Their friend lived 6 miles from their house on the same road. How long did it take them to walk there the first time? Well, it took them 2 hours. How long did they stay at their friend's house? Looked like from 2 to 6 hours, so that's a distance of 4 hours. How many hours did it take them to walk home? Looks like 3. I could ask you some other questions about how fast they were walking. How were they going faster or slower on the way there or on the way back? Well, I can read that one of two ways. It took them only 2 hours to walk the 6 miles on the way there. It took them longer to do it on the way home. So a longer time would mean a slower speed. Well, what exactly speed did they walk? Well, on the way there, looks like they were going 6 miles in 2 hours. In fact, they went 3 miles every hour, and so their speed during this entire time was that same thing, 3 miles an hour. Notice we're talking about the slope. What about on the way home? It looks like they walked home 2 miles every hour, but notice that we would say the slope is negative. The importance of the negative sign is the direction. They're moving in the backwards direction this time. Yeah, so I'm able to get all of those things from this one picture of the distance compared to the time graph. And so this is a function, and we typically refer to this as the position measuring function. It tells you the when and the where. It tells you when and where the object is. Okay, so literally to evaluate the position function, like position function value at 3 is 6. The position function we often call S, and S of 3 is 6. That tells me at the time 3 hours, the position of the object was 6 miles from the starting point, or 6 miles from 0. Okay? So notice when we talked about how fast it was going, we were talking about the slope of this graph. And so once again, I could talk about average speed or average velocity compared to the instantaneous velocity. So for example, on a particular time interval, we could do average velocity. Like during this entire first 2 hours, it went 6 miles. And so the particles or objects average velocity is 3 miles per hour, because that's the slope along this entire section. Now, that would also be the instantaneous velocity, because if at any of these times, because if, for example, at the 1 hour mark, the tangent line to this graph is going to be the same as this line is here. Okay, but the average velocity would be defined to be the average rate of change on a particular interval of this graph. So let's describe the how fast part in a little more detail now. Notice I can tell how fast my object is moving at any time along this 9-hour stretch, because at any point along this path I can tell you the slope. Now there's two exceptions to that. I'm not necessarily going to be able to tell you the slope right at these sharp corners. So everywhere else, if I put my dot on any point, I can read the slope, and that would in turn be the speed or velocity in miles per hour. And I can see that on this first stretch, it's moving at the same rate the entire time. It's going 3 miles every 1 hour. And so now I've got another graph labeled on the Y scale, miles per hour, which is the velocity or how fast. And I've got the same 9-hour stretch here. But during these first 2 hours, the person walked exactly 3 miles per hour the entire time, except for maybe right here. I'm just going to leave a hole there. The person stayed where they were for 4 hours. And the slope of this graph is 0, so their velocity or how fast will be indicated by 0 miles per hour. When the person was walking back to where they started, they were going 2 miles every hour, but they're going in the other direction. The slope of this section would be mathematically considered to be -2. And so that's considered the velocity of the object during those 3 hours. So notice the positive and negative of the slope indicates the direction of motion. So during the time when they were moving to the forward direction, the velocity is a positive 3 miles per hour. When they're not moving at all, their velocity is 0 miles per hour. And during the part where they went home, walked to the other direction, their velocity was -2 miles per hour. So here we're plotting those values as the y coordinates of the velocity, but that was the slope of this graph. So of course, we're going to make the connection to calculus here, and since we're describing the slope of this graph, this velocity function v has to be defined in terms of derivatives to be the derivative of this other function, the position function. Now in turn, now in this case, we could ask the follow-up question: during the time when the object was moving, were they changing speeds at all, or were they going the same speed the whole time? In this one, the slope is constant, and so they technically were not changing speeds at all. They were going 3 miles per hour this entire way. However, in real life, that really doesn't happen. You can't walk forever or even a great distance at a constant speed. There would normally be some speeding up and slowing down. So maybe the graph instead would go kind of like this. We would start off at a much slower rate or slope, and then gradually increase it, and maybe stay at a somewhat constant speed for a while and keep the slope kind of constant. But then at the end, when we get ready to rest, we're going to have to gradually slow down, and indicating by this gradual decreasing of the slope to 0. Okay, so in this situation, the velocity or slope of the graph is not staying the same. It's gradually increasing for a while, then maybe gradually decreasing for a while. And so we can measure that too, because there's a bit of a difference. Say, let's change the story a little bit from going 0 miles an hour to 60 miles an hour in 30 seconds in a car. That would be pretty easy to do and wouldn't be a big amount of acceleration. But it's a big difference between that and going 0 to 60 miles an hour in 5 seconds. There's way more acceleration and changing of the speed. And so we can indicate that we can describe that too. That would be described by noticing if this velocity graph is changing its value. Or in other words, the slope or rate of change of the velocity, which is called the acceleration. So let's summarize this with making a list of the 3 characteristics of motion that can be described with equations like this. The first is our position measuring function. And I usually label the position function S, and it tells me the when and the where. It tells me where the particle is and when it is there. And the typical units, I'm just going to make a little column here. Things like how many feet did it move? Or how many feet from from 0 is it? Maybe meters, maybe miles. Typical linear measurements. Okay? Now, the position obviously can change. As soon as the particle starts to move, the value of this function changes. But the question is, how fast is it changing? That's the velocity. So the typical name for the velocity function is function v, but in terms of calculus, it's the rate at which the position is changing. And so that would be the slope or derivative of the position function. It's going to tell me how fast. Okay, so the numerical value tells me how fast it's changing, but the numerical value also tells me the direction. Because if I get a positive number for this velocity value, the particle is moving away or forwards away from the where it was. And if the velocity gives a negative number, the particle is moving to the other direction, to the left. So because it's the slope of the function measuring feet compared to hours or seconds, a typical unit might be things like feet per second. Maybe if it's miles and hours, maybe miles per hour. Another pretty common one in the metric units is meters per second. Okay, because remember the position function measures distance and time. And so now the slope of that graph measures distance over time. Now, your velocity need not be the same all the time. You can speed up, you can slow down, you can go from 5 meters per second to 7 meters per second. Or you can go from 5 meters per second to -3 meters per second. In either of those cases, your velocity is changing, and so the acceleration measures that. So the acceleration measures the change in the velocity, or the velocity's derivative. But you see where this is going. The velocity was in fact the derivative of the position function. So we could in fact label this as the second derivative of the position function. This tells me things like, is the velocity changing? Okay? And by how much? Well, so that would be the rate at which the unit up here is changing. So if it's feet per second for the velocity, then the acceleration might be measured in feet per second, or miles per hour. Now this can be condensed down to things like feet per second squared or miles per hour squared.